Hey everyone, let's talk about linearization. So you've probably seen this in your math classes, but it pops up a lot in AP Physics. And it's really just a tool that we use to make predictions. So why do we linearize? We want to build a model, or, well, we want to make a mathematical model. That is just a fancy word for equation, because that mathematical model or equation allows us to make predictions. And that's really a main goal in physics, is to be able to look at data, collect data, look at data, analyze it, and make predictions for the future. So before we get started, there are 4 main functions that you must know going forward in physics. You have to be able to look at the shape of a graph and be able to identify what type of relationship we're looking at. So the first one is, let's say we have y and x. This is simply a linear graph. This can also be called a direct proportion. It's not just a direct relationship, because direct relation means as one increases, the other increases. This one is a direct proportion because it is linear, and it's only direct if it goes through 0, 0. So this would be like the parent function, y equals x. The way we would talk about this, we would say y is proportional to, I'll only write is proportional to out once, is proportional to x. And so we can also say y equals mx plus b. We will be looking at this, y equals mx plus b, over and over and over throughout the year. So make sure you understand that we know m is our slope, b is our y-intercept, and then y and x, those are what's on the y and x axis. So there's our first function that you should know. It's already linear, so we don't have to make it linear. I can directly write an equation for a straight line, y equals mx plus b. Our next one, though, is not linear, so we have to do something called linearization to make it linear so that we can make a model. Now, you probably recognize that as a quadratic function. That's the most basic, y equals x squared. So that tells us y is proportional to x squared. It is not proportional to x anymore, because if it was proportional to x, it would be a straight line, but it's not. Because it is quadratic, that means it's proportional to x squared. So there's a modification that has to happen. Instead of graphing y versus x, we will graph y on the y-axis. There's no modification there, but instead of x, I will put x squared. That means I'm going to take all my x values, so the numbers that are on this axis, I would square them, and then I would have a linear graph. So our mathematical model now, because the first graph was not linear, we cannot use y equals mx plus b. But now our second graph is linear, so we can say y equals m. Now it's not x, it is now x squared. And then plus b is our y-intercept. So that's what our relationship would look like. So we have linear, we have quadratic. The next one you must know is an inverse relationship. If you look at a graph and you see that it's going down like this, we can see that as x increases, y is decreasing. Okay, that's an inverse relationship, what we just looked at with the patterns worksheet. This is also called an inverse proportion. We see that y is proportional to the inverse. Inverse is 1 over x. So if you have a graphing calculator, if you do 1 over x in your first function and graph it, you'll see that it looks like this. Now, it's not linear, so we have to make an adjustment. Instead of x, we need to graph 1 over x. That's the adjustment we need to make. So 1 over x will go here, and y will go there. And now it is linear. So our equation would be y equals m times 1 over x plus b. Notice it's still the same, like y equals mx plus b. But when you change your x values, you need to put that in place of the x variable. The last one we need to look at, and that is y and x looks like this. So think about what relationship this is. This is called a square root function. Okay, y is proportional to the square root of x. Now, sometimes, I don't know why we do this, apart from maybe we don't like dealing with square roots in functions. A lot of people will say y squared is proportional to x. So both of those are true when we're looking at the square root function. Think about what that means we need to graph. We need to graph y and the square root of x to get a straight line. That would be, oh no, go away. That would be y equals m times the square root of x plus b. Or, because we also have this second statement here, we could graph y squared on the y-axis and x on the x-axis. And that would still be linear, and we would write a function that would be y squared equals mx plus b. Notice that whatever you change is how you write your equation. So these are the 4 functions you need to know. One more, I guess like an honorable mention. If you see a graph like this, that is no relationship. And we would just say y equals b. Notice the slope is 0. Okay, so we're going to practice linearizing. I'm going to do 4 questions with you, and then you will have 4 to do on your own for these next couple of pages in your packet. But the good thing is this takes up a good chunk of your packet. And so getting this done, you'll be almost done with your summer work. So for each data set, we're going to graph the data, identify the relationship, graph the modified data, and then write a literal equation. All right, our first piece of data. Now, it is annoying that we're graphing this by hand. However, I'm making you do this because the AP test, you have to graph by hand. So it's good practice. It's tedious, but it'll be fine. So we have pressure and volume. Now, the good thing about the AP test is that it actually provides you a nice graph. All right, we're working in this first quadrant here. We have x and y, which is volume and pressure. So I want to make sure I have it labeled with the actual variables. We're not interested in x and y. This isn't a math class. And pressure will go on the y-axis in pascals. And our biggest volume is 10. You want to make sure you're using up as much of the graph as possible. So I'm going to go up by 1, so that seems easy enough. Okay. You can probably put it on like double speed here while I'm graphing. And our biggest pressure is 40, so I'm going to go up by 5s. So that would be 10, 20, 30, 40, 50. Oh, I really didn't use my graph as good as I should. I'm going to actually maybe, I'm going to do this. 5, 10, 15, 20, 25, 30, 35, and 40. So a few things when you're graphing. Your scale, we have to start at 0. So in physics, unlike maybe bio or some other sciences that you've done, we are not allowed to show breaks in our graph. So you can't do anything like this, 0 and then a break and then 5, 6, 7, 8 like that. Okay? Or maybe something more obvious might be like 20, 22, 24. Like we can't do breaks like we can in other classes. Because if you're doing a break, then you're not going to see the true picture of your data. So you want to make sure these spacings are the same. Like if I have 0 to 1 here, I couldn't do 1 and then my next one be 5. Each one has to be 1 in length. Okay, so I'm just going to graph my data. So I'm going to go over 0.1 and up to 40. That's really, based on my graph, it's going to be really close to right there. 0.5 and 8, that's about right there. It's going to be really hard to graph this bottom data, and that's just how it's going to be. 1 and 2, 4 and 1, 5 and 0.8. You can hardly even tell it's getting closer to 0. That's okay. 8 and 0.5, and then 10 and 0.4. It looks like a flat line. Oh. If you had like Excel or something, then it would do a much better job of graphing this. But let's look at this relation. If you go back and look at the graphs we just did, if you're not sure what shape that is an inverse proportion. We see it looks just like this one here. That's an inverse proportion. So the modification required, I want to go ahead and name this graph. This is an inverse relationship. The modification required, instead of graphing pressure versus volume, I need to graph pressure versus 1 over volume, the inverse of volume. So now let's look at our data. This is where we make a new column of data. And instead of graphing volume, we have to graph 1 over the volume, which has units. Instead of meters cubed, it's 1 over meters cubed. So here we're going to do 1 over 0.1 is 10. 1 over 0.5 is 2. 1 over 1 is 1. 1 divided by 4 is 0.25. 1 divided by 5 is 0.2. 1 divided by 8 is 0.125. And 1 divided by 10 is 0.1. So now we're going to take our new data and graph it. So our biggest x value now is 10, and we'll keep the same scale for our y. So we still have pressure on the x-axis in pascals, but now we have 1 over the volume, 1 over meter cubed, and we said our biggest volume was 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and our biggest pressure was still 40, so 10, 5, I'm making every 2 blocks be 5. 5, 10, 15, 25, 30, 35, and 40. Okay, it's not perfect, but it'll get the point across. All right, so we're going to go to 10 and 40. 10, kind of right here. 40, that's going to be kind of like right here. And then we have 2 and 8. So I'm going to go over to 2 and up to 8, about right here. 1 and 2. Notice I'm graphing all of this data now. That's my new x value that I'm graphing. So 1 and 2, 1 and 2, 0.25 and 1. This is going to be really hard to graph. 0.25 and 1. 0.2 and 0.8. Ooh, honestly, all of that is going to be kind of like stuck in this little corner, so it's just getting closer and closer to 0. On an AP test, you would actually be able to see it better, but now you can see that I have a linear relationship. I linearized my data. So now that it's linear, let's go ahead and find the slope. My trend line definitely goes through 0, 0. So my slope is going to just be rise over run. So 40 pascals over 10 per meters cubed. So if this was 1 over meters cubed would come up here. So there's my slope. 40 over 10, that equals 4. Now we can write our equation. So my literal equation is, instead of y and x, we have to use what's on the y-axis, which is pressure, equals slope. We're taking, in case you're not following, we're taking y equals mx plus b, and we're giving meaning to it, essentially. So pressure is on my y-axis. My slope was 4. And what's on my x-axis? Volume is not on my x-axis. 1 over the volume is on my x-axis. And then plus 0, because my y-intercept, or b, is 0. You don't have to write the 0 there, obviously. You can just leave it as, you could also write it like p equals 4 over the volume. So that shows you how you can go from an inverse relationship, a picture that you really don't, I really don't have an equation for this. I don't have a perfect way to model it. So to make an equation, we make it linear. Because being an inverse proportion means that y is proportional to the inverse of our variable. And when you hear the word proportional, like we said up here, proportional is linear, or especially like a direct proportion. All right, let's look at data set 2. I might just do 2 with you, honestly. Maybe I'll do 3. I don't know. All right, so, I didn't give you variables here, so I had to make them up. This will be time, and this will be distance in meters. All right, sketch the original graph. My biggest time is 5 seconds. 1, 2, 3, 4, 5. And if you don't want to do like all the little dashes, you don't have to. It's just important that you use up as much of the graph as possible. So you don't want to have like all 1 through 5 stuck right there in that first little section of the graph. All right, we have to get all the way to 75. I think I'll go up by 5s. $40, $45, $50. There we go. All right, we have 0.1 and 0.03. That's basically 0, 0. 0.2 and 0.12. Oh, these are so hard to show. 1 and 3. I know it's not quite where it should be. If I had a true grid, maybe I could make it look better. But these numbers are so small, it's kind of hard to see. Oh no, I erased things. Distance. Okay, 2 and 12. 2 and 12, that's about right here. Also, just a pro tip here, the bigger you draw your dots, the more likely they'll go through your line of best fit or trend line. When we're not playing connect the dots. I'm not going to try to hit every dot. I'm just showing a trend. 3 and 27. So that's going to be like 27, about there-ish. 4 and 48. Right there. And then 5 and 75. Okay. Hopefully you see a trend. And for me, it definitely doesn't look linear. If we go back and look at the notes we just took, that's a quadratic relationship. It's that curve upward that we see. So what modification do we need? Instead of graphing y versus x, we have to graph y versus x squared. Or I guess we're not using y. We're using, I didn't label my graph. Oh no. Make sure you have your graphs labeled. We need distance here in meters because that's on my y-axis, and we need time here in seconds because that's what's on my x-axis. So we're going to graph distance, I'll use d, versus t squared. That will make it linear. So you're going to come up here and you're going to make a new calculated column. Oh my gosh. And this column will tell you what to graph. So we're going to do t squared. If it was seconds, now our unit is seconds squared. So 0.1 squared is 0.01. 0.2 squared is 0.04. 1, 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So we're going to take our new data and graph it. So this is my new x and y. We didn't change y, but x has changed. So now my x value, the largest x value I'm dealing with, is 25. So let's sketch our linearized graph. 5, 10, 15, 20, 25. Okay, this is going to be time squared and seconds squared. Yes. And then we didn't change our distance. And our biggest distance was 75, so I'm going to keep that scale. There we go. Okay. So instead of me going back and forth, I'm just going to look at my reference sheet here. But I'm graphing t squared on my x-axis. I'm going to go over to 0.01, and then I'm going to go up to 0.03, which is going to be kind of hard to get these first few points. All right, so over 0.01 and up 0.03. That's basically right here at 0, 0. Then we have 0.04 and 0.1. Again, that's like almost right on top of each other there. 1 and 3. Ooh. That looks like 2.5 and 3, but that's okay. If I could zoom in on that corner, I would, but I can't. All right, 2 and 4. Can't get that point either. Or sorry, it's not 2 and 4, it's 4 and 12. Okay, 4 is right here-ish, and 12 is going to be like right above the 10 right there. Okay, and then we have 9 and 27. 9 and 27, maybe right here. If you need to draw those dotted lines to help you line things up, go for it. 16 and 48. 48's here-ish. And then 25 and 75. And you can definitely see that we have a much more linear graph now. I can draw a linear trend. And it looks like I'm going through the origin here. So I'm going to use that as part of my trend line to help find the slope. So now we can calculate the slope. My slope is going to be 75 meters. I didn't put my units there. Meters over 25 units of seconds squared. So 75 over 25 is 3 meters per second squared. Now we can write our equation. Instead of y equals mx plus b, we're going to write a literal equation. So think about what's on our y-axis. That would be distance. So I'm going to put d equals my slope, which was 3. 3, oh no. Okay, I was trying to be nice and neat with the colors. Obviously that failed. That's going to be my slope. Then we have to look at what's on our x-axis, which is time squared. It's not time, or it's not, it's not just time anymore. Another thing I want to point out, guys, make sure that in your literal equation, you're putting the variable, not the unit. The unit would be what's in the parentheses, like seconds or pascals or meters cubed, things like that. Make the variables are what you're actually measuring, like distance and time. So this is going to be 3t squared, because we squared our time, plus 0. Or we can just write d equals 3t squared. We don't have to have the 0 there. So every problem is the same. You're going to sketch your original graph, figure out what you have to do to change your variable, and then graph a linear graph. I think maybe I'll just do one more, and then I will let you do the rest, because I know this video has already taken up a while. Okay, let's sketch our graph. We have mass on our x-axis in kilograms, velocity on the y-axis in meters per second. I'm going to graph my original graph. My biggest mass is 8, so I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. And my biggest velocity looks like 22.4, so I want to do, I'm going to do by 4s. 4, 8. You could go up by 5s. I just like 4s when we're dealing with lots of even numbers. I feel like it's easier to find. 16, 20, 24. Okay, so we have 1 and 22.4. Probably there somewhere. 2 and 19.6. 3 and 16.5. Oh, darn it. I actually didn't want to do this example. 4 and 13.3. It'll be fine. 5 and 10.4. It's going to be somewhere like that. 6 and 7.7. 7 and 4.6. Then 8 and 1.1. So if you look at this, the trend line is pretty linear already. That doesn't mean it's a proportion, because they're not both increasing, but it is linear. Sometimes this is called an indirect proportion, not an inverse, but an indirect. So what we'll do, there's no modification required because it is already linear. None of the others should have, none of the others should be like this. All of the others should have some type of modification. But since this is no modification, let's go ahead and write the equation. This tells us that velocity equals some slope times the mass. M is mass, not M as slope. Velocity, mass. We just need to find our slope here. My line of best fit, I want to say that my y-intercept, I'm going to say that this line is on my trend line and this line is on my trend line. So my slope is negative 24 over 8. That's negative 3. So my equation would be V equals negative 3 times the mass. There was no modification. All these others should require modifications. So I know this is a longer video. If you have questions on any of these problems, please reach out and group me, message me. It's nothing for me to hop on here and explain a couple of these questions. So I'd rather you reach out if you need help than being clueless and saying it's too hard and I can't do it, because you can't do this for sure. Like I said in the packet, yes, we are going to move quick, but I'm here with all the supports.